Hello, and welcome to Astronomy for Sleep, a quiet place to drift through the universe at an unhurried pace where the language stays gentle and the night feels wide and safe. Tonight, we are going to soften a headline that often arrives with sharp edges, the kind of headline that tries to sound final and dramatic. Scientists say Big Bang was wrong. If you've ever seen those words and felt a quick spark of confusion or alarm, you're not alone. They sound like a door slamming, like a cornerstone being pulled out from under modern astronomy. But the real meaning, the meaning scientists actually intend when they speak about the Big Bang in a critical or questioning way, is almost always calmer than the headline. It is not usually a claim that the entire modern picture of the universe has collapsed. It's far more often a claim that the picture is being refined, tested, and perhaps extended in a few specific places where new measurements are so precise that they reveal small mismatches. The story is not one of collapse. It is a story of precision pushing a successful model to reveal where it might be incomplete, and that is something science is built to do. It is the difference between saying a lighthouse is fake and saying the lens inside it could be improved so the beam is clearer, farther, and more accurate. The Big Bang model, as used by working cosmologists, is not a fragile story. It is a strong framework supported by multiple lines of evidence, and strong frameworks do not shatter when questioned. They evolve, and the questions themselves become part of their strength. To understand what scientists actually mean, it helps to begin with a calm, accurate picture of what the Big Bang idea is in the first place, because the popular image of it is often not what cosmologists mean at all. In everyday imagination, the Big Bang is pictured as an explosion, a blast of matter flying outward from a point into empty space, as if the universe began inside a pre-existing dark room. In modern cosmology, that image is misleading. The Big Bang model is not about an explosion happening at a location in space. It is about the expansion of space itself. When astronomers say the universe is expanding, they mean that on large scales the distances between galaxies are increasing over time because the fabric of space between them is stretching. If you reverse that stretching, you arrive at an earlier universe that was denser and hotter. The Big Bang model is at its heart a history of cooling and expansion, a universe that begins in a very hot, very dense state, then expands and cools, allowing different physical processes to occur at different times, like chapters opening in sequence as temperature and density drop. It is a framework that describes how the universe changed from a nearly uniform hot plasma into a cosmos filled with galaxies, stars, planets, and the quiet chemistry of life. It's not a single firecracker moment, it's a long unfolding. This framework rests on several sturdy pillars that work together, and it is worth letting them feel steady before we move into the areas where headlines become dramatic. The first pillar is expansion itself. When astronomers measure the light from distant galaxies, they find that the light is shifted toward longer, redder wavelengths. This is called redshift. The simplest way to feel what redshift means is to imagine a wave being stretched. If the space a wave travels through stretches while the wave is in motion, the wave's wavelength becomes longer. In the universe, this stretching happens on large scales, and the more space the light has traveled through, the more it has been stretched, so the greater the redshift tends to be. Over the last century, this relationship between distance and redshift has been mapped with enormous care. It is not a subtle effect, it is a dominant feature of our observations of distant galaxies. It tells us that the universe is not static. It is expanding. The second pillar is one of the quietest and most beautiful signals in all of science, the cosmic microwave background, often called the CMB. This is the faint afterglow of the early universe light that has been travelling since the cosmos was young. Long ago, the universe was so hot that atoms could not exist as stable neutral structures. Matter was in a plasma state. Electrons and nuclei were separated, and light could not travel freely because it scattered constantly off the charged particles. In that era, the universe was opaque like a bright fog. As the universe expanded, it cooled. Eventually, it reached a temperature low enough for electrons to combine with nuclei forming neutral atoms, When that happened, light no longer scattered so easily and it began to travel through space. That freed radiation has been traveling ever since, and because the universe has continued to expand, the radiation has been stretched into longer wavelengths, cooling into the microwave range. Today, that radiation fills the sky in every direction, nearly uniform, with tiny variations that carry the imprint of early fluctuations. It is like a soft background whisper that arrives from everywhere at once, a relic of the time when the universe first became transparent. The third pillar is the abundance of light elements. In the first few minutes of the universe's history, temperatures and densities were high enough for nuclear reactions to occur throughout space. This era is called Big Bang nucleosynthesis. The universe cooled too quickly for heavy elements to form in large amounts at that stage, but it did produce large amounts of hydrogen and helium along with traces of deuterium and lithium. Measurements of primordial element abundances in environments that preserve early composition broadly match the predictions of this early nucleosynthesis process. These element abundances are not an afterthought. They are a strong independent check on the early hot universe picture. Together, expansion, the cosmic microwave background and light element abundances create a coherent story. They are not three separate ideas loosely glued together. They are three different windows on the same physical history. That is why the Big Bang framework is so widely accepted. It is not accepted because it is a pleasing narrative. It is accepted because multiple independent observations align with it. So when you hear a Big Bang was wrong, it is very rarely a claim that these pillars are gone. It is far more often a claim that the most commonly used specific version of the model, the standard cosmological model with its particular ingredients and parameters, might be incomplete when we demand very high precision. In other words, the broad Big Bang framework can be right while some details in our most popular model need adjustment. And it is exactly this kind of adjustment that science has always done with successful theories. A theory can be spectacularly useful and still be an approximation to something deeper. To understand why this kind of headline has become more common, it helps to appreciate a simple fact: cosmology has become a precision science. For a long time, astronomers knew the universe was expanding, but measuring exactly how fast it expands, how its expansion has changed over time, and how different forms of matter and energy shape that expansion was difficult. Measurements were uncertain. Error bars were large. When error bars are large, many values overlap and models can appear to agree, even if they hide subtle inconsistencies. As technology improved, surveys grew and analysis methods sharpened, and those error bars shrank. Precision has a peculiar effect. It turns vague agreement into crisp disagreement. When two methods disagree by a small amount, it might not matter when uncertainty is large. But when uncertainty becomes tiny, the same small disagreement becomes statistically significant. This is how tensions appear in science. A tension is not a contradiction in the dramatic sense. It is a persistent mismatch between measurements or between measurement and model prediction. Tensions are signals that something deserves attention, either a hidden systematic effect in measurement or a missing piece in the model. They are not death sentences, they are invitations. The most famous of these invitations is called the Hubble tension, and it revolves around the present-day expansion rate of the universe, a number known as the Hubble constant. There are different ways to measure this number, and in a simple universe where the standard model is correct and measurements are fully understood, these ways should agree. One approach measures the expansion rate directly in the nearby universe by using objects that act as distance markers. Astronomers find objects with known intrinsic brightness, measure how bright they appear, infer their distances, and compare those distances to redshift. This approach is often called the distance ladder, because it builds distance estimates in steps using nearby calibrations to reach farther scales. Another approach uses the cosmic microwave background. The microwave background encodes information about the early universe's content and geometry. When cosmologists fit the microwave background patterns with the standard model, they infer the expansion rate today as part of the best fit parameter set. The CMB method is not measuring the expansion rate directly today. It is inferring it from the early universe under the assumption that the model connecting early and late times is correct. For years, the expansion rate derived from the microwave background has tended to come out lower than the expansion rate measured locally with the distance ladder. The mismatch is not enormous, but it is persistent. If it were a simple mistake in a single dataset, it might have vanished as the methods improved. Instead, it has remained stubborn enough to become one of the central puzzles in modern cosmology. And this is one of the main sources of the Big Bang was wrong headline. But the headline is imprecise. The debate is not whether the universe expanded from a hot early state. The debate is whether the simplest standard model connecting early and late times includes all relevant physics, and whether all measurement methods are free of hidden biases. Another area where discussions can become headline-friendly involves the way structure grows in the universe. The early universe had tiny fluctuations in density. Over billions of years, gravity amplified these fluctuations, pulling matter into a web-like structure of filaments, clusters, and voids. There are multiple ways to measure how clumpy matter is today on various scales, including gravitational lensing, which is the bending of light by mass and galaxy surveys that map the distribution of galaxies. In some analyses, the amplitude of structure inferred from early universe data differs slightly from the amplitude suggested by some late-time observations. This kind of mismatch is another possible tension. It is more subtle and complex, and it changes as datasets and methods evolve, but it adds to the sense that the standard model may be under precision pressure. Again, the story is not that the Big Bang framework is useless. The story is that we are testing the model at a level where details matter. A third source of dramatic reporting comes from observations of very early galaxies. When we observe very distant galaxies, we are looking back in time, because light takes time to travel. Powerful telescopes can reveal galaxies from very early epochs, sometimes when the universe was only a fraction of its current age. Some early observations have suggested that certain galaxies appear surprisingly massive or bright at very early times. This can make it seem as if galaxies formed too fast, challenging certain expectations. But it is important to recognize that this kind of surprise often leads to refined astrophysics, rather than a rejection of the Big Bang. The early universe was a complex environment, and the conversion between observed light and inferred mass depends on assumptions about stellar populations, dust star formation histories, and many other factors. As models improve and more data comes in, initial surprises often become understandable. Sometimes they remain intriguing and push astrophysical models to evolve, but they rarely overturn the broader cosmological framework. So what do scientists mean when they say something that gets translated into Big Bang was wrong? Often they mean something like this. Our standard cosmological model, often called lambda, CDM, may need modification. Lambda represents dark energy as a cosmological constant, a smooth energy density that accelerates expansion. CDM stands for cold dark matter, an invisible form of matter that does not emit or absorb light, but influences gravity and the growth of structure. Lambda CDM is the simplest model that fits a remarkable range of observations from the microwave background to galaxy clustering to supernova distances. It is successful, but a model can be successful and still be incomplete. Saying it might be incomplete is not a rejection of the Big Bang. It is a suggestion that the details of the universe's components might be slightly more complex than our simplest assumptions. There are several kinds of modification scientists explore. Some explore whether dark energy might not be constant but could vary with time. Others explore whether there might have been an extra energy component in the early universe, sometimes called early dark energy, that could change the inferred expansion rate from the microwave background without ruining the fit to other data. Others explore whether there are additional light particles or subtle interactions in the dark sector, the part of the universe involving dark matter and dark energy. Others explore modifications to gravity on cosmological scales. Each of these ideas must clear a high bar. It must fix the tension without breaking the many successes of the standard model. That is difficult, which is why no single alternative has taken over. The standard model remains the best working framework. The field is exploring its edges. At the same time, an equally plausible category of explanation is that one or more measurements contain hidden systematic effects. A systematic is not simply a mistake. It is a bias or uncertainty that arises from the method itself, from calibration steps, from selection effects, from assumptions that are shared across analyses. In local distance measurements, there are many steps where subtle biases can enter: dust extinction, crowding and blending of stars, calibration of standard candles, selection of galaxies, and more. In microwave background inference, there are issues like foreground emission from our own galaxy instrument noise beam characterization and analysis choices. In galaxy surveys, there are selection effects and modeling assumptions. Because these measurements are difficult and complex, it is possible for small systematics to persist even in careful work. One reason tensions are interesting is that they can reveal these systematics. If the tension turns out to be a hidden bias, the result is not disappointing. It is still progress. It means we've improved our measurement methods and refined our confidence. This is why the dramatic language wrong is not very helpful. In science, a model being wrong can mean many things. It can mean it is completely false, which is rare for a model as widely tested as the Big Bang framework. It can mean it is incomplete, which is common. It can mean it is an approximation accurate in many regimes, but not all. Newton's laws of motion are wrong in the sense that they are not the final description of reality. They are an approximation that fails in certain conditions where relativity matters. Yet Newton's laws remain extremely useful and accurate for most everyday scenarios. In the same way, even if lambda CDM requires adjustment, it can remain the correct effective model in many contexts. Wrong often means not the whole story. There is also another confusion that headlines feed the difference between the Big Bang model as the description of early expansion and the philosophical idea of a cosmic beginning in an ultimate sense. The Big Bang framework describes the universe back to very early times, and it implies that the universe was once extremely hot and dense. But it does not necessarily claim to explain what in absolute terms began the universe, or what happened at an initial singularity. In fact, most working cosmologists treat the singularity that appears when equations are extrapolated too far back as a sign that our known physics is incomplete at extreme conditions. The Big Bang framework works extremely well for a vast span of cosmic history, but it may not be the final word about the earliest possible moments. Discussions about what happened before a certain time or about mechanisms like cosmic inflation can be misrepresented as the Big Bang was wrong, when the reality is that scientists are refining the earliest chapter, not rejecting the evidence for a hot early universe. Inflation, for example, is a proposed period of extremely rapid expansion very early in cosmic history. It was introduced to explain why the universe appears so uniform on large scales, and why the geometry is so close to flat, and it provides a mechanism for generating the tiny fluctuations that later grew into galaxies. Inflation is widely studied, but its details are not fully settled, and there are competing models and alternatives. Debates about inflation can sound to outsiders like debates about the Big Bang itself. In reality, inflation is often treated as an extension of the Big Bang framework, a possible mechanism that sets initial conditions. Scientists are still testing and refining it. The existence of debate does not mean the Big Bang framework has failed. It means cosmology is addressing deep questions where data is subtle. Now, because you want this to be a long, restful video, it can help to slow down and follow the life cycle of how a dramatic claim becomes a headline and then becomes a calmer reality. A scientist writes a paper. The paper might say something like, "Our results suggest a tension with the standard model at the level of such and such sigma." In scientific culture, that phrase is careful and bounded. It says there is a mismatch and it quantifies it. It does not say the entire framework is false. But outside scientific culture, the word tension can be interpreted as crisis. The paper might say, this may hint at new physics beyond lambda CDM. Outside the field, the phrase beyond can sound like replacement rather than extension. The paper might say, if confirmed, this could require revision of the standard cosmological parameters. Outside the field, revision becomes wrong. The public layer compresses nuance into drama because drama travels faster. But in the research layer, the pace is slower. Measurements are checked. Independent groups test them. New observations are collected. Alternative analyses are performed. Confidence grows or shrinks. Over time, the field moves toward clarity. That process is not loud, but it is steady. If we look at the Hubble tension as a central example, it becomes easier to see why the story is not a simple verdict. There are multiple independent methods to estimate the expansion rate. Beyond the traditional distance ladder using certain types of stars and supernovae, there are methods involving gravitational lensing time delays where a distant variable source, such as a quasar, is lensed by a massive foreground galaxy, creating multiple images. The light paths have different lengths and pass through different gravitational potentials, so changes in the source appear at different times in each image. By measuring these time delays and modeling the mass distribution of the lens, scientists can infer cosmological distances and estimate the expansion rate. There are methods using different kinds of standard candles, such as the tip of the red giant branch. There are methods using maser galaxies where water masers in disks around supermassive black holes can provide geometric distance measures. There are methods using baryon acoustic oscillations combined with other probes. There are even emerging methods using gravitational waves as standard sirens, where the signal of a merging neutron star system provides a distance scale. Each method has its own strengths and weaknesses. As these methods improve, they provide cross-checks. The long-term goal is not to declare the Big Bang wrong. The goal is to understand whether the expansion rate mismatch is real and if it is what it implies. If it is real and not due to systematics, then cosmology may need a new ingredient. But even that would not erase the Big Bang framework. It would likely mean adding a subtle component that changes the way early universe physics connects to late universe measurements. Early dark energy is one such idea. The basic thought is that if the early universe had a brief additional energy component that influenced expansion before recombination, it could alter the calibration of distances inferred from the microwave background, effectively shifting the inferred value of today's expansion rate. This is an elegant idea, but it must fit many constraints. It must not distort the microwave background patterns in ways we do not observe. It must not ruin the successful predictions of the standard model for other data. That is why it is difficult. Yet the exploration itself is valuable. It pushes cosmologists to understand what kinds of new physics are even possible without breaking what already works. Another category of ideas involves interactions within the dark sector. If dark matter and dark energy interact in subtle ways, it could change the expansion history. Another category involves extra relativistic particles in the early universe, altering the radiation content. Another involves modifications to the physics of recombination, changing how the CMB is interpreted. Another explores modified gravity. The fact that so many options exist is not a weakness. It is a sign that the universe can be probed in many ways and that our models are flexible enough to be tested. If, on the other hand, the tension is due to hidden systematics, then the outcome will be a refinement of measurement methods. That is also a satisfying scientific result. It would strengthen confidence in the standard model and improve the reliability of cosmological measurements. In either case, the field moves toward a clarity. Science does not lose when it finds a systematic. Science wins because it has improved its understanding of how to measure the universe. Another restful way to think about this is to consider what it would mean for the Big Bang framework to be truly wrong in the dramatic sense. We would need an alternative explanation for the cosmic microwave background that matches its near-perfect black-body spectrum and its pattern of tiny fluctuations. We would need an alternative explanation for light element abundances that match observed ratios. We would need an alternative explanation for the expansion and the way redshift relates to distance. We would need an alternative framework that explains the growth of structure and the distribution of galaxies on large scales. That is a very high bar. It is not impossible for science to shift paradigms, but for a framework supported by multiple independent pillars, complete collapse is unlikely. More likely is refinement. In the history of science, when a powerful framework is challenged, it is often not discarded but embedded inside a deeper one. Newtonian mechanics became a limit of relativity. Classical thermodynamics became part of statistical mechanics. Classical electromagnetism became part of quantum electrodynamics. Each older framework remains useful in its domain. The newer framework explains why it works where it works and where it fails. If cosmology finds new physics, it will likely resemble this pattern. The standard model will become the limiting case of a deeper model that reduces to it under certain conditions. Now, because we are in the gentle atmosphere of astronomy for sleep, we can let the story become less about argument and more about the universe's quiet consistency. Whatever tensions exist in our measurements, the sky remains. The cosmic microwave background still arrives from all directions, carrying the imprint of a young universe. Galaxies still show redshifts that increase with distance. The universe still appears to have an age on the order of billions of years, consistent with stellar evolution and cosmic history. The basic Big Bang picture is not a fragile story that can be undone by one surprising paper. It is a broad and deep framework. The surprising papers, the ones that get transformed into headlines, are often about details, the exact value of the Hubble. Constant. The precise properties of dark energy, the small differences in structure growth, the earliest galaxy formation rates, the fine-grained interpretation of the CMB. These are important and exciting, but they do not erase the foundational evidence. It can also be calming to remember that the universe is not obliged to be simple. Humans love simple stories. We want the universe to have a single clean equation, a single clean number for expansion, a single clean explanation for every parameter. But nature can be slightly more complicated than our first best model. The standard model of cosmology is often praised for its simplicity, a universe with ordinary matter, dark energy, and a set of parameters that describe expansion and initial fluctuations. That simplicity is part of its beauty. But the universe might have extra subtlety. Dark energy might not be constant. Dark matter might not be entirely cold and collisionless. There might be additional particles. There might be small interactions. If so, it is not a failure of human understanding. It is a discovery. It means the universe is richer than our simplest picture. In that richness, there is no threat, only more to learn. Now imagine the work of cosmology as a quiet night shift. Researchers receive data from surveys and telescopes. They calibrate it. They compare it to models. They check consistency. They run simulations. They look for biases. They talk to colleagues who use different methods. They publish results with careful language. Then the public layer translates it into dramatic words. But the actual work remains patient. It continues night after night, year after year. Over time, the field converges. Some tensions fade, some persist, new ones may appear, but the overall picture becomes clearer. In that sense, the phrase Big Bang was wrong is more like a momentary splash of loudness over a fundamentally quiet process. There is another angle worth exploring gently because it often gets tangled with the headline. Sometimes people hear Big Bang wrong and imagine that the entire concept of a beginning is being challenged, that scientists are suddenly claiming the universe had no beginning, or that it existed forever in its current form. In reality, the relationship between the Big Bang model and the concept of a beginning is subtle. The Big Bang framework describes an expanding universe that was hotter and denser in the past. If you extrapolate the equations backward far enough, you reach conditions where the equations predict infinite density, a singularity. Most scientists interpret that not as a literal physical point of infinite density, but as a sign that our current physics is incomplete at those extremes. We do not yet have a complete theory that unifies quantum mechanics and gravity, a theory that would be needed to describe the earliest moments with confidence. So scientists can question what happened at the very earliest times without rejecting the hot early universe evidence. They can explore ideas like bouncing cosmologies, emergent cosmologies, cyclic models, or quantum gravity effects that remove the singularity. These are deep topics. They can sound like the Big Bang is wrong if simplified. But even in many of these alternative ideas, the universe still goes through a hot, dense phase that resembles what we call the Big Bang. The disagreement is often about what happened before that phase or how it began, not about the evidence for the phase itself. This is why if we want to translate the headline into a calmer sentence, we might say something like this: scientists are investigating whether the standard cosmological model which describes an expanding universe with dark matter and dark energy needs refinement because some high-precision measurements do not agree as neatly as expected. That is the real meaning most of the time. It is not that the universe is no longer expanding or that early universe relics no longer exist. It is that cosmology has become so precise that small mismatches stand out, and the field is working to understand whether those mismatches arise from new physics or from subtle measurement issues. Now let the mind settle into a gentle visualization, because this can help turn the idea into something restful rather than sharp. Imagine the universe as a long, slow, cooling lake of light and matter. At the earliest times in our description, everything is hot and dense and light cannot travel freely. Then the universe expands and cools. At some point it becomes transparent and light begins its long journey. That light becomes the microwave background still present today. Meanwhile, matter begins to clump under gravity. Tiny fluctuations become larger. The cosmic web forms. Gas falls into dark matter halos. Stars ignite. Galaxies grow. Heavy elements are forged in stars and spread through space. Planets form from those elements. Life emerges on at least one planet. In this story, the details can be debated: the exact expansion rate today, the exact behavior of dark energy, the precise growth rate of structure. But the broad story remains. The debates are about the fine-tuning of the map, not about whether the landscape exists. And because your goal is a 25 to 30-minute audio, it is worth extending this calm explanation with a little more gentle depth, the kind that fills time while staying soothing. Consider how difficult cosmological measurement really is. We cannot pick up the universe and measure it with a ruler. We infer distances across billions of light years by reading light. Light is the messenger, and it is filtered by many layers: interstellar dust, intervening gas, the limitations of instruments, the choices of surveys, the statistical methods we use. When we measure the brightness of a supernova, we must correct for dust and for differences in supernova properties. When we measure Cepheid variable stars, we must calibrate their relationship between pulsation period and brightness. When we measure the microwave background, we must subtract emission from our own galaxy and other sources. When we map galaxy clustering, we must account for selection biases and model the relationship between galaxies and underlying matter. Every step is careful. Every step is a potential source of subtle bias. The fact that cosmology has achieved the level of precision it has is remarkable. It is also inevitable that at this level of precision, small mismatches will appear. It does not mean the universe is inconsistent. It means our methods are reaching the point where the remaining uncertainties and complexities matter. In fact, one of the most restful lessons in this story is that scientific knowledge is not a fragile tower built on one plank. It is more like a woven fabric. Each thread supports the others. The Big Bang framework is supported by many threads. If one thread shows strain, the fabric does not immediately tear. Instead, scientists look at that thread and ask why it is strained. Is it fraying because it is pulled by new data? Is it fraying because it was tied incorrectly? Is there a missing thread that should share the load? This is how science remains stable while still being open to change. It does not leap to total rejection, it investigates. So when you encounter the headline again in the future, you can let your mind translate it automatically into something calmer. You can hear scientists say Big Bang was wrong and quietly replace it with scientists are investigating tensions in precision cosmology, and some are exploring whether the standard model needs refinement. That is the true grounded meaning far more often than not, and it is not alarming. It is the normal frontier of measurement. As we drift toward a softer ending, consider that the Big Bang model has already been refined many times. Early versions of cosmology did not include dark matter as we understand it now. They did not include dark energy. They did not include the detailed physics of recombination and the precise interpretation of microwave background anisotropies. Over time, as new observations appeared, the model evolved. It grew richer. It accommodated new components. Each addition was not a death of the Big Bang framework. It was an improvement in how well it matched reality. If new physics is required now, it will likely be another refinement of that kind, a subtle addition that makes the picture more accurate. If the tensions are resolved by understanding systematics, that too will be a refinement, a better measurement, a clearer calibration, a more reliable map. In both scenarios, the universe remains what it is, and our description becomes better. And in the quiet spirit of astronomy for sleep, it is comforting to remember that the universe is not a puzzle that must be solved tonight. It is a long story and we have time. The stars will keep shining while scientists measure and remeasure. The microwave background will keep arriving faint and steady. Galaxies will keep drifting apart across expanding space. Our models will keep improving. The dramatic headlines will keep flashing, but beneath them the real work will remain calm. So you can let the phrase Big Bang was wrong lose its sharpness. You can let it become what it truly is, a shorthand for an ongoing careful effort to understand the universe at higher and higher precision. It is not the end of cosmology. It is cosmology doing what it always does at the edge of knowledge, listening closely to the sky, noticing where the numbers do not quite align, and patiently asking the universe for the missing piece. Now as the pace slows further and the night deepens, you might imagine that missing piece, whatever it is, as something small and elegant rather than dramatic. Perhaps it is a slight change in how dark energy behaves. Perhaps it is a subtle interaction that only matters early on. Perhaps it is a calibration detail waiting to be corrected. Perhaps it is a new method that will bring two measurements into harmony. Whatever it is, it will be discovered not by panic, but by patience. The universe rewards patience. It speaks in faint signals, in long data sets, in repeated patterns. And we on this small planet have learned to listen. Let that be the calming thought to rest with tonight. The Big Bang is not a fragile myth that can be overturned by a headline. It is a strong framework built on multiple lines of evidence, and the current debates are about refinement at the level of precision, not about the disappearance of the universe's early light. The sky remains steady. The story remains broad. The details are being tuned. And in that steady, careful tuning, you can let your mind relax, knowing that even when scientists argue about the universe, they do so with measurement, with caution, and with a deep respect for what the night sky has already taught us.